So, we've been doing millimeter wave surveys for a while now, and we keep calling them CMB experiments. I don't think that helps. I think we should just call them millimeter wave surveys that you can do CMB with, or you can do more astronomical things. Yeah, and so we always show these maps. Like here's the Planck map, and you see like there's this sort of stripe through the middle, and it's great. It's nice that we can do the CMB. I'm very happy for that, and that's what I spend a lot of my time doing. But this is actually a 143 gigahertz map. So already you see that there's this galaxy in there. There's a mission that even at high latitude. There's a lot of stuff going on in that sky. And then you say, okay, so what are we working towards? Well, here's the CMB, here's the SPT map. And you see we didn't do a huge chunk of sky, but it's 2,500 square degrees. So this thing right here is the SPT pole patch. 3G's not on here. It's basically, here's what we're talking about with S4. So this is the plan. So, let's make a map. So we can't, so from Chile you can't see the entire sky, but from Chile, so this is a possible survey, and you can see the big chunks of the galaxy. There you see the ecliptic going through. So it's a huge swath of sky. And in fact, if you look at the sky area should be comparable, if not a little bit more than what LSST is going to do. So we're talking about doing these very wide area millimeter wave surveys, scaling up to over half the sky. So we've already done some, but 2,500 up to 20,000 is a big step.
What's the rate of repetition? How many times will this sky be looked at?
Well, that's an open question. So I hope Ido will tell me how often we should. So this is what we're working on for S4. So the current plan, what we're trying to do is see if we can do something approaching this footprint every 2 days.
Because that's useful for gravitational wave sources.
Yeah, if they're right in the millimeter. Yeah, so or for gamma ray bursts, or for who knows what else is up there, right? So it'd be nice if we could do as much of this as we could every 2 days. That's kind of what we're working, that's our aspiration right now. So, there's problems like there's this, the sun. So that gets in the way, so that, punches some holes, so you can't do the whole thing. But, even then, like we can observe during the day, so we can do most of this footprint. So there is a strategy, where someone has shown that you could go every 2 days over this footprint and basically hit all of our early universe goals as well. So it seems like we can do it. There's a strategy. So we'll see. Right. So there you see the ecliptic going through. So you can't see it on this patch. So this is a different spin, but there's the galaxy. The ecliptic actually doesn't really go through the South Pole Telescope patch. So at this point, we haven't done very much solar system science with the South Pole Telescope. Just because this is 40 degrees of deck is this line right here, and then you say just at 23.5 degrees, the ecliptic doesn't get down. So a lot of the solar system stuff we currently can't do with SPT. All right, so what does the data look like? So these are the highest resolution. Sorry, these are the most sensitive high-resolution maps that are around right now. So remember, there was that split. There was the low resolution and the high resolution. SPT was on the left side of that plot. If you go to the left-hand side of the plot, you say, what is all the stuff that has been published? SPT pole. So here's just the intensity map, and then this is the difference map. You see it's very high signal noise. Here's the Q and U polarization. And so what you see is, so then these are just the raw maps. So I think there have been a couple of super bright sources that may have been masked, although I don't even think they've been masked here. So these are just the maps. And so what do you see? Well, hopefully you can see a bunch of stripiness in this polarization map and a bunch of just kind of like foam in this map on the left. So the foam here is the cosmic microwave background, and in fact that's what all these stripes are in the map. And this box, these cross-hatched herringbone patterns, that's also the cosmic microwave background. And you would say, well, that's a pretty weird looking pattern. I think a reasonable person could look at that map and say, are you sure you did that right? But what you're seeing is just the fact that the cosmic microwave background has some weird symmetry to it, which are these E modes and B modes. So this weird thing you see here are exactly the E modes. So if you take some random spin 2 field, you can split it into two components, E modes and B modes. E modes have the property that if you start with the polarization direction being like this, and you say which way does it change? Well, it can only change in the direction that's either perpendicular to that. So here you see if it's aligned this way, and it's changing in this direction, or you could have it be aligned this way and have it change that way. But that's what an E mode is. It's comparing which way that polarization pattern is changing compared to what that local polarization direction is. With a B mode, you see that's not true. You see the polarization direction is here, but it's changing in this direction. Or the polarization is this way at 45 degrees and it's changing. So if it's changing in a way that's at 45 degrees to the polarization pattern, that's a B mode. And so what's going on here? Well, this is Stokes' Q. So Stokes' Q is this way versus this way. And so when things are changing either along those directions or perpendicular to those directions, you get that. Stokes' U is tipped over at 45 degrees. That's why you see this herringbone. So there, in principle, should actually be a little bit more structure in the horizontal direction, but we filtered that out as part of our scan in the Q mode. Okay. So the reason the CMB is this way is because we are dominated by just the scalar fluctuations. People talk about tensors and scalars. So the density fluctuations are the scalars. Those are what are sourcing the polarization. So if you have density, if this was some intensity fluctuation in the photon field, and then you're going to generate polarization, well, if it's varying this way, then you're going to generate polarization that's in this direction or in this direction for a pattern that's like this. So if your local photon field is varying this way, the polarization that results from the scattering of that intensity field will have to be either straight up or down or 90 degrees. So that's why scalar fluctuations will only generate an E mode. And so when you look at this map and you say, oh, well, I see all this sort of herringbone structure down here, what you're doing by eye is you're saying that the primary fluctuations are predominantly sourced by just regular scalar fluctuations. Now, that's not the only pattern you could have. There could be B modes. And in fact, as we all know, so gravitational waves can generate both E and B. And it depends on, and that's because you have this extra degree of freedom, which is the polarization of the gravitational wave as it's propagated. So because gravitational waves can generate both E and B, that means that you can use the CMB B modes as a diagnostic for primordial gravitational waves, and that's what John Kovac's leading the world in. All right, so if instead you take those Q and U and you turn them into an E map, the E map looks like this. The B map looks like this. This is an E difference map, but this is what our B mode map looks like right now, which is to say it's still consistent with noise, not at the power spectrum level. In the power spectrum, we see an excess due to the lensing-induced B modes, but we don't see any gravitational waves. All right, so what do you do with this? Well, so this is one of the motivations for these experiments is that you measure these power spectra, you do some very precise measurements of the details of the acoustic peaks, and that'll tell you, so for instance, here, so these are the B modes, and I said, well, it's consistent with noise, but it is true that you take this pattern that you start with, and imagine if you put a little deflector in the middle of this pattern, it's going to sort of move these things out in some direction that's spatially dependent. So you can take some E mode, and if you gravitationally lens it, it'll generate some small amount of B. And so that's what you can see right here. So there's some small amount of B that's just coming from lensing, and you can actually predict that based on what you see in the E modes compared to what the expectation is for the gravitational potentials. Here are the lensing B modes. These are the SPT measurements. Here are the bicep Keck measurements. So these are these large angular scale measurements, and you see they measure these B modes really well. And then the question is there an excess of B modes down there?
So if there was no lensing,
yeah,
there would still be B modes from the second order.
Yes.
Right?
Yeah.
That would be like a couple of orders length down.
Well, people argue, so I think Cora has spent some time thinking about this. So for instance, from reionization, so there's differential screening, and then there's also rescattering from the bubbles of reionization, and those can give you some signal which typically are a little bit below this signal for most models. So I don't know if you could rule out all of them.
So it's just an order of magnitude below?
Below the lensing B mode, certainly out here, yeah, there should be maybe an order of magnitude. It should be detectable. So people are running, you know, we have, so postdoc at UIUC is Chang Feng, and so we've actually spent some time trying to think about whether you can run, you know, whether you can detect those signals in cross-correlation with large-scale structure. So we've been looking for that. Like, it's at the level where people are looking to detect it. So instead of thinking of it as a contaminant, you should think of it as a signal we can measure.
That statement is true at high L, at L at 100, where the B mode searches are. I think.
So down here, so the reason I'm not absolutely sure is because, so could you come up with some model where you had some giant bubbles that you've placed very carefully? It's not. So there is some level of large angle where it might be able to pop up, but it's pretty unlikely that you wouldn't detect it some other way. So I don't think you should think of those higher order contaminants as a unknown foreground for the primordial gravitational waves. I think you should think of them as something that could be going on out here that's a really interesting signal to measure. All right, so where was I? Good, so we want to measure R. So one of the things, so John, I'm sure that John Kovac says the letter R probably 100 times a day. So just to give you a sense of the scale of this experiments and where we're going. So currently, here's the upper limit from BICEP-Keck